So next up on our list of things to be able to compute with a continuous random variable is expected values, right? And when I say expected values, I include things like the variance and so forth because the variance is an expected value, right? Now, just as a reminder, so just to recall, if x is discrete, right? Then we define the expected value, let's say, of any function of x. So let's say g of x, right? As this summation, right? So as long as g of x is well defined on the sample space, so this function exists for all values of x in the sample space of my random variable, then we define the expected value as this, where it's the sum. You take each possible value of x, evaluate it in your function, and then you multiply it by your PDF and then sum all those products and you get a number, right? Well, I mean, if we're essentially saying that, when we move to a continuous random variable, that anything that's expressed as a summation for the discrete random variable will now be expressed as an integral for the continuous one. So then we can immediately update this definition, right? So it follows that if x is now continuous, right, then the expected value of any function, again assuming that this function is well defined on the sample space, right? Or let's say for all real values of x. So let's have that be our blanket statement. So then again, what would we do? Well, we would replace the summation with an integral, and again, to cover all possibilities, we would say this integral goes from negative infinity to positive infinity, and we would take whatever our function g is, multiply our PDF, and integrate that from negative infinity to positive infinity. And again, assuming this integral, let's say it is an improper integral, if the improper integral converges to a number, then we would have a finite expected value of this function, right? So then it means if, for instance, I just replace g of x with x, if g of x is equal to x, then we end up getting our regular expected value or mean, right? So in particular, in fact, we can just write down all the things that we know about the mean and the variance at this point. So in particular, if g of x is simply equal to x, then the expected value of x is defined this way. The integral from negative infinity to infinity of x times f of x dx, right? And so then we could also say if g of x is equal to x squared, then we could compute the expected value of x squared by taking a similar integral, but now multiplying x squared and f of x and then integrating that, right? So therefore, and we can use the same definition that I guess I should say the same alternative definition that we gave for the variance. So this implies that the variance of x is the expected value of x squared minus the expected value of x squared, right? So all these carry over. The only difference is now we're going to be doing integrals, right? And we might remember, there are certain types of functions where when we multiply by x, we might have to use a slightly more advanced integration technique, right? Integration by parts, for instance, comes to mind, right? Now, so just for completeness, I will state the other formula for the variance. Now you might remember this, so alternatively, so now I'm calling the first definition the alternative one, but they're all equivalent, right? That's why we can use either one. Remember that the variance of x is the expected value of x minus the mean squared, right? Well then, yeah, if I now look at this squared deviation from the mean as my g of x, then I could define the variance this way, right? So well, now it becomes little. So little x minus mu squared times f of x dx. I would say, though, very rarely do we use this form, right? We tend to find these tend to be easier to work with, especially for integrals, because, for instance, down here, working with the quantity x minus mu squared means I'm going to have to FOIL out and do a bit of algebra, multiply by my function, and then do an integral, as opposed to up here, where you're simply either multiplying by x or multiplying by x squared. So algebraically, these tend to be a lot easier in the case of the continuous random variables, right? All right, so let's do an example of this. And I think for this one, I'm going to break the trend and give an example of a PDF where the sample space is not 0 to 2. So I'm going to go out on the limb now and go 0 to 1. Right? So that's our PDF. And again, 0 otherwise. And let's go ahead and compute the expectations and the variance. In other words, we're going to find the expected value of x, the expected value of x squared, and then that will allow us to find the variance, and then the standard deviation is defined the exact same way. All right, so let's take a look at this. So our expected value of x. Now in this case, again, because the only interval of x that has a positive probability associated with it is from 0 to 1, again, I won't have to worry about the negative infinity and the positive infinity, because on those intervals from negative infinity up to 0, the function is 0. And then from 1 to infinity, again, the function is 0. So this expected value is the integral from 0 to 1, right? And then you take our variable x and multiply the PDF. So 3 halves 1 minus x squared, and then dx. And then we integrate this. Well, we can factor out the 3 halves. We don't have to, but that tends to be a useful trick every now and again. So factor out the 3 halves and then distribute the x. So that gives me x minus x cubed. And then we have a power function. So we'll use our power rule for antiderivative. So this gives me 1/2 x squared minus 1/4 x to the 4th from 0 to 1. And what do we have here? So we got 3 halves. At the upper limit, we have 1/2 minus 1/4. So that's 1/4. So yeah, let me write that in. So 1/2 minus 1/4. And then at the lower limit, we have 0. And then, so this is 1/4 times 3 halves. So that's 3/8. And we interpret this um, uh, expected value the exact same way. So again, we haven't really talked about, like scenarios that could lead to these random variables. Right now we're focusing more on the process. But if there is a continuous like measuring process that will give us values between 0 and 1, like you're measuring the depth of something or the area of something, and you continue to get values between 0 and 1. If you continue that measuring process indefinitely and average all the measurements that you observe, then that average again is going to converge to 3/8. So it's still a long run average. That's still one way you can interpret it, right? Now let's find the expected value of x squared. And again, what's nice about this is, when you think about what went into this process, the only thing that's different now is just that I'm going to have a square there, so my powers are going to be a little bit different, my fractions are going to be a little bit different, but not much difference at all. We have, like, fundamentally, we're really doing the same thing, just with a slightly higher power of x. Take out the 3/2. I'll go down so it doesn't get in mixed up with that. So 3/2. Now distribute the x squared. So that gives us x squared minus x to the 4th dx. Here's our 3/2. Again, use our power rule. So we have 1/3 x cubed minus 1/5 x to the 5th. From 0 to 1. At the upper limit, what do we have? We have 1/3 minus 1/5. And then at the lower limit, let me write my brackets here. At the lower limit, again, we have 0, right? So if we use a common denominator of 15, this is 5/15 minus 3/15. So that's 2/15. So I have 3/2 times 2/15. Well, that gives me 1/5, right? So this is the expected value of x squared. It's 1/5. Now to find the variance, right? So we're going to use this formula to find our variance, the expected value of x squared minus the expected value of x squared. So the expected value of x squared is 1/5. And the square of the expected value is, so what do we have here? 3/8 squared, which is, so we got 1/5 and then minus 9/64. So what can we use for a common denominator there? Well, looks like we're just going to have to multiply these, so that will give us 320. So this will be 64/320 minus 45/320. So 64 minus 45, so that's 19. So that's 19/320. So that's my variance. And as usual, the standard deviation is always the square root of that, right? And just as a general rule of thumb, if you get to your variance and you get something negative, something is amiss, right? Can't have a negative variance. And then, so our standard deviation is the square root of 19/320. All right. So, I mean, that's pretty much it as far as the expected value and the variance and the standard deviation. Now, I want to do another example where the sample space is infinite in the sense that it doesn't go from a number to a number, right? So let's do another example. And let's say this is my PDF of a continuous random variable. And let's say it is c over x squared. Actually, let's make this x cubed. And now x is greater than 1, but there's no upper bound. So let's say from 1 to infinity, that's now the sample space, right? And then 0 otherwise. All right, let's see if we can go through, figure out what my constant is. That's a c, right? So let's see if we can figure out what the constant is that makes it a valid PDF, and then compute the expected value of that, right? So part A in this question, what is C, right? And part of the reason for doing this, I want to show you that, again, there's a lot of the material that would have been covered in your second semester of calculus that we are using quite a bit here, right? So in this case, since anything less than 1 would have a probability of 0, right? So associated with it. So what we can say is the integral of this function, so from 1 to infinity, of c over x cubed, let me write that, my curly x, c over x cubed dx, that has to be equal to 1. Now this is an improper integral, and remember, for improper integrals they are defined as limits, so we are going to use a limit here to compute this. So this is an improper integral, right? And by definition, for this improper integral, it's the limit, and we tend to use b as our placeholder for the upper limit from 1 to b. Now I'm going to rewrite this and use so I can use my power rule. So I have c times x to the negative 3 dx, and that has to be equal to 1. Now for the constant, I can factor out the constant, right? And then I still have my limit. Now let's do our antiderivative, add 1, so it becomes negative 2, and then divide by negative 2. So I have negative 1/2 x to the negative 2, and then I'm going to evaluate that from 1 to b. Again, that has to be equal to 1. So now I can also factor out the negative 1/2. So I can put negative c over 2 in front of my limit. And then at the upper limit, I'll have b to the negative 2 minus 1 to the negative 2, which is just 1. So we have this. We got a 1 there. And now we take our limit. Now with the negative exponent, I find that it helps quite a bit if you rewrite this as 1 over b squared, right? And then you can see that as b gets very, very large, this fraction here, so the 1 over b squared, that approaches 0, right? So then, yeah, so this improper integral, it does converge. So what do we have here? We have our negative c over 2 times 0 minus 1, so that's negative 1. That has to be equal to 1. So c over 2 is equal to 1. Therefore, c is equal to 2. All right? So we've figured out what the constant has to be for this one. But again, part of the reason for doing this example is to remind you of what is expected as far as an improper integral, right? So because my upper limit is infinite, then we're going to express it as a limit, do our antiderivative, use our fundamental theorem, compute our limit, and then we're able to solve for our constant. All right? Okay. So remember, we got our constant to be 2, so I'm going to go back over here and do part B. Right? So let's find the expected value of this thing. Right? So now this, again, our domain, our sample space here is infinite in length. Right? So we know that, in fact, let me write that in, so that C is equal to 2. So to find the expected value of the random variable whose PDF is given by this function, again, it's going to be an improper integral because we have to integrate over all possible values of x, here from 1 to infinity. And the function now is the 2 over x cubed, but then I have to multiply by x. So I have to do x times 2 over x cubed dx, right? So let's simplify and also write down our definition for our improper integral. So 1 to b, we have 2 over x squared dx. Factor out the 2. Rewrite it so I can use my power rule. So that's x to the negative 2. Right? Then apply my power rule. And that gives me negative x to the negative 1. Then apply my fundamental theorem. So, and this just as we did in fact right over here, that's why I'm kind of doing them in parallel, just to show you again how similar the process is and what is expected. And then we have the limit as b goes to infinity. So b to the negative 1 is 1 over b. 1 to the negative 1 is 1. So there's our fundamental theorem. And then the last thing we do is compute the limit. So this is negative 2 times, this also approaches 0, right? So 0 minus 1. So the expected value for this random variable is 2, right? So even though, right, even though this sample space goes from 1 to infinity, the expected value, this long run average, is going to be 2. Now, if you graph this particular PDF, you'll see why, right, this happens. So for instance, so when x is equal to 1, this function has a value of 2, right? Because you'll have 2 in the numerator, 1 in the denominator. So it starts here. But then what happens is, as x gets very, very large, this denominator gets very, very large. So the fraction gets very, very small. So this function approaches 0, the horizontal axis, very quickly. It never gets there, right? It's a horizontal asymptote. But what happens is you have the majority of the area. So this would be 2, right? So you have the majority of area, like in this interval here. The larger the values of x are, the less likely that x will be in any of these intervals, right? So even though the interval itself is infinite, right, our expected value is finite, and it's a relatively small number, right? So I think that those are two good examples to kind of to think about, and to just as a reminder of what is expected as far as being able to evaluate not just finite integrals but also these improper integrals, right? See you in the next video.